A very warm welcome from our side here from Schlotau and Bauer to a new webcast. We are really happy that you joined us today.
First of all, as you might have noticed, Lisa is kind of structured as your everyday, similar to your everyday Microsoft Office application. We have these ribbons up here where the different tools and modules are organized. So you find tools for the configuration of the intersection, meaning everything that is hardware out there that you want to configure, like the topology of the intersection, signal groups, and so on, detectors, public transport, detection chains, and stuff like that. Then there's the planning part where you do the calculation of time parameters and defining offsets and so on, defining stages, stage transitions, signal timing plans, and time switch or the automated timetable. And there is also a module for unsignalized intersections. We have the coordination view, the time distance diagram. As I said, this would be license M in our new licensing model, and the OMTC part, so everything related to traffic actuated, the test site, and the logic editor in the Lisa XL. And we have this upload section where you can upload data directly to compatible controllers. We have a counting module, and of course, several support tools. Please ignore the ENIS ribbon. That is something internal. So first step, we're opening the project management page. This is where all my Lisa projects are organized by intersections and by cities. So if a city has several intersections, I can all assign them a certain location default because, certain locations or cities differ in the way that they calculate intergreen times, in the way that the types of signals that they are using. So it makes sense to organize your projects by cities. First thing you do here is define a new intersection. We'll just call it intersect 1. And the variant is 0, 1. And once I have defined this variant, I get access to all the kind of meta information that is important for an intersection. Of course, the way I named it, what project it belongs to, the guideline that I want to use. So the default is always using the German guidelines. From our experience, this guideline is kind of encompassing most of the functionalities that you could need. There might be some differences to certain countries. These settings that you can see here, like Netherlands, Poland, Czech Republic, Denmark, Israel, and so on, they all include these changes that we had to make. When you go into the detail, you're always finding that it always comes down to where is actually the collision point? How do you deal with the entering vehicle, with the leaving vehicle? What are the different speeds? But we'll come to that. If your country is not listed here and you're not happy with what the German guidelines have to offer, then we have to take a look at it and maybe find a way to make certain changes. Usually, you can get very close just by changing the settings in the intergreen time calculation module. I don't want to go too much into detail. There is a lot of technical stuff here. There is management stuff here about the status. I could talk half an hour about everything that you see here, so let's just get started. If you have any questions specifically, just write them down in the chat. Maybe we could mention there is a map. When you have a map server or you want to see this on OpenStreetMap, you can configure an OpenStreetMap server somewhere here, and all the intersections that have coordinates attached to them will appear here on this map. Other than that, there's no scheme yet because we haven't put in any data. If I would go to some other intersection here, then we would find more or less how they look like, but ours is empty, so that's why there's nothing there now. So what's the first thing we have to do? We first have to tell Lisa the topology of our intersection. So what our goal is, we want to have a signal timing plan. For that, we need signal groups, we need intergreen times, minimum green times. And in order to get the intergreen times, we need the topology. We need to know where conflicts are. We have to determine which conflicts are actually relevant. And when we've done all that, then Lisa can do its magic and do the calculations. So the first step, depending on where in the planning process you are, is either loading a site plan. We'll do that right after I showed you this, or is loading a template, because imagine you're somewhere in the planning process where you don't actually have a site plan yet. Someone has told you, well, we're actually in a pre-study phase. We want to know if it makes sense to have, I don't know, 3 lanes, 4 lanes, 2 lanes, separate left turner or not. And then you could use one of those templates, do a signal timing plan for that, evaluate it and say, okay, it would rather make sense to have one more through lane or stuff like that. So this is just in case you don't have a site plan yet. We are going to use a site plan. I see, this is how it looks. Depending on how big it is, you might want to crop it a little bit because the smaller, better, something like that. And now we're asked to enter a scale. There are 2 ways to enter a scale. One is just, somebody was so nice to leave this scale over here. So that would be 20 meters. Or you could also, I don't know, use any distance on the intersection where you do know how long it is. Maybe this. So this should be something like 975 or 984. Yeah, it's more or less what we see here. Or third possibility is you have these reference points where you have geo coordinate like GPS or European coordinate system. These 2 are supported right now. And if you define the positions of these 2 coordinates, you can set the reference points here, reference point 1, and down here, reference point 2. They don't have a geo coordinate right now, but it would be possible to just enter it here. Depending on the system, you have to give a bit more information. And then Lisa is capable of just calculating the scale out of the relation of these 2 reference points. Without further ado, let's enter the data that we're going to enter here is first of all the legs, then the lanes in each leg, the movements between these lanes, and after that, the crossings. That is the topology. And then what we can also enter here graphically are the signal groups, detectors, detection points. First of all, to define a leg, I draw it with the leg tool from the inside to the outside, and then I automatically change to the lane tool. Defining lanes is easily done just by clicking on the middle of the lane, desired position. Here I do the same. 1, 2, 3 lanes. And now you see here I have the stop line that Lisa is seeing right over the stop line that is in the site plan. Here, this is only true for one of these lanes. And this one, I still have to move it and can just select it, move it up here. And now I brought the stop line to where it actually is on the site plan. While I'm doing this, I can bring up an intersection diagram, which is now empty because I haven't saved anything yet. When I save it, you can see it's showing me these 2 legs that I have defined so far. And as I go along, this schematic site plan should update. One, two, three. You see this way. Here in this little window, I'm seeing everything that is Lisa seeing so far. So if there's something in here, something missing in here, then I have to add it in the site plan view. Let's go on with the 4th leg. Now this is just a leg without lanes. Now that I add the lane, they also appear here. This plan. First lane also has to be moved up a bit. And now we can go on, define the movements between them. So that is as easy as just connecting an entrance with an exit. So I'm now with the trajectory tool here. Looking for the shortcut. Oh yeah, it's P for path, travel path. Once they are connected, you can click on this radius that is automatically created by Lisa and just move it. I could leave it like this or leave it like that. It's just a click of a button on this box. And another possibility would be, if I go backwards, to do it with certain waypoints like this. For example, if I wanted people to turn that way, not really realistic, but I could do that. So if you have, I don't know, a construction going on. You see also these movements are updated up here in the schematic view. So it also makes sense if there is more than one possibility to turn. To connect them all. So Lisa is also considering these paths, calculating the intergreen times. Of course, it will always pick the one that is the crucial one, the relevant one, the one that would lead to the highest intergreen time. But we'll see that later when we go into the calculation. So this right turner, and then I should be good. Let me double check again here. So we have through, right, left, through, right, left, through, right, left. So it's all there. That's good. So now we can talk about right of way. We can also put that in here. I'm just marking the axis and say, okay, this is a Main Street. You see here this little symbol for Main Street. And now I can tell the secondary direction to yield. Also so nicely shown in the schematic up here. What about different types of traffic? So we have transport modes up here. Right now it's set to vehicle. We could add a bus here. You can see that the outline is changing to a blue color. This means now it's a mixed vehicle and bus lane. If I take out the vehicles or the cars, like individual vehicles, then it would turn all blue, indicating that's the bus. Tram would be a darker blue. Bicycle lanes would be all red. In a case like this in Germany, you would have to consider bicycles on all movements, or at least on all movements that go into the right lane, because bikes are probably not supposed to be on the left lane. So now we would have to go through all these movements and add the bicycle, because this is pretty common to happen. There is a possibility to just right click into the background and say we add transport mode bicycle for all movements. And now we can just go on like that. If I want to be really exact, I would take them out for these right lanes, left lanes better. That's what I wanted to say. So this one, this one, this one. There are no bikes here and here also. So this is how you change transport modes. Let's see. Now we go into defining crossings. Crossings are similarly defined like legs by pulling, clicking, and holding, and pulling the middle line. And now we can just adjust these points in the corner. Wherever you see this little box in this module here, you can move the box, moving radiuses, moving the endpoints of a crossing. And this way, Lisa knows exactly where the conflict zone with the pedestrians is supposed to be. And here you see already these conflict points, right? When I click here on, and of course you can also turn this into a bicycle crossing if you wanted to, depending on what the purpose is. We've now dealt with all the geometry in order to get to the point where we can calculate intergreen times. For intergreen times, of course, we need signal groups. And for Lisa to be able to calculate these signal groups, we also need to define which signal group is responsible for which stream or which movement. And to facilitate this process of defining signal groups and assigning them, we can just do it all in one step. We just have to mark the corresponding lanes or corresponding paths in case it is a signal that is just for one direction and not for the whole lane. And now that they are marked, I just click on the plus and add a signal group vehicular 1, vehicular 1L for left turners. There are certain types that you can allocate. These are like German standard types vehicles, vehicle green and yellow, vehicle red and yellow, pedestrians, and so on. We will later see where to define other types in case your type is not covered by this standard. Let's do first this allocation. Painted 2, 3. And you see up here, whenever I do a definition, it also shows it here in the lane. So again, I'm having full control about what I'm doing. And if I should get something wrong at this step, there's always the possibility to do corrections later in the list. We're going to take a look at the signal group list right after this, also at the detector list. So in order to add the detectors, same thing, you can just mark a lane and go to the detectors tab. Maybe we finish the signal groups first because we haven't done the pedestrians yet. So for that, mark a crossing, and this is going to be P2. And this crossing is P3. And this one is P4. And there's also a blinker there, icon, a yellow flashing to indicate that turning vehicles have to wait. I'm going to leave out any acoustic signals for now because we don't want to make it too complicated. And I'll close this. As for detectors, same dialog down here. Different tab, mark a lane, hit the plus, aim the detector D1. There are different types that we can choose from. Inductive sensor loop in this case. Define a distance. I think this is about 35 meters, and a length. And also defining the function that the detector is going to have, because this was going to have an impact later. Would be extension, 35 meters, and so on. I will not go through all the detectors now because I think you get the idea. You can also move them around later when you mark them. You have these, as I said, wherever you see these boxes, you can move something. And with that step, we're basically done here. Maybe something that I want to show you. If you are using this data also to deploy a roadside unit, right now, Lisa is one of the few softwares in which you can actually create these maps of the Car2X communication. It's a data form that is used by the roadside unit to send to incoming vehicles the topology of the intersection. And you can use Lisa to create such map data. That is why you can extend and shape these lanes for as far as you want. If I probably zoom in a little bit more. And of course, you can also connect lanes by clicking the end and just connecting it here. And now this is the connection point between these two lanes. So the good thing about this is you don't have to use a different tool for creating this map data. It has been tested. It is being used in, for example, in Hamburg, different cities in Germany. Hamburg has already deployed over 200 intersections this way and created the map data within Lisa. So it is a tested tool for that. Next step. So we have signal groups now. Let's have a look what we did there. This is the list. As I said, if I had made any mistakes, I can correct the name or the position in the list and I'm not satisfied with that. Also change the symbols here that are being used. Initiation and termination time, like how long, how many seconds of red and yellow, how many seconds of yellow, depending on the speed. Minimum green times, minimum red times. Let's put in minimum red, minimum green time, I think is something that we should do. Also for the pedestrians, something like 10 and 12 seconds should do. And maybe change the symbol for the yellow flash so we know that this is not a pedestrian. Then some definitions later to facilitate the definition of an initiation and termination program. So what is off? What is supposed to flash when the signal is off? Stuff like that. And I mentioned before, in case these signal types here are not enough for your needs, here is the list where you can define new signal types, where you can go into detail, like what color indications are actually allowed, how many phases does the signal head have, what are the signalization states, and what switch commands are needed for the operation of this signal head. Here you also should keep in mind what happens when I switch on and off. There should always be all possibilities to go to the unlit state, stuff like that. And this is already pretty advanced. So also you only have to do it once. Every time you're planning for a new city, you can save your work as the location default that I mentioned in the beginning, and then all local changes that you had to do for city XYZ, whatever it may be, can be reused the next time, of course. Facilities, maybe just really quick. So this is just for documenting the hardware that you're using. Like we just defined the signal group, and then now here we can define the signal heads that are actually connected to the signal group. You can define auxiliary signals like present signal for a bus. You know, when you have bus prioritization, there's this small signal indicating the driver, yes, you're registered, or anything else, the little red light on the push button, for example, everything that is not safety relevant but still controlled by your controller should appear here. You can define poles to document where the signal heads shall be. And then now you see I have two signal heads now for V1. And here everything that has to do with the signal head, what signal indication should be put there. For example, for these left turners, you might want to put the arrows here and see how the actual mask should look that is put in front of it. We have special masks here. If you have, these are usually used for, I don't know, some tourist advertisement of German cities. They have these special solutions. If you want something in here and Lisa, then we're going to make it happen. Just send us the graphics. Here, by the way, the list of the detectors. Detectors, as I mentioned here, the three that I have defined. It's a bit same like the signal group table. You can give additional information for the functioning of the detector, define some parameters laid for the traffic actuated mode, and so on. To get into the planning, as I said, signal groups, we have defined them. We have also assigned them to a certain travel path. We know where these travel paths meet, where the collision points are. So Lisa knows which signal groups do actually have a conflict zone. Now we have to define which of these conflicts are actually relevant. Not all conflicts will lead to these two signals not being able to be going to green at the same time, because sometimes you have this thing like a parallel pedestrian will be able to can go at the same time. So we have to define this manually here. So, and that is something that you could argue that could be done automatically, probably. And Lisa can actually find all the conflict zones and all the conflicts and put them in this matrix, but then you would still have to take out those which are not actual conflicts. This is by design because this matrix here is the core safety feature of the controller. It is what the engineer is responsible for, is what he has to sign off for. It is also, it's a liability issue. Like if we would include this feature in Lisa and it would just be a press of a button, when something goes wrong, then it would be probably our fault and not the fault of the engineer, even though he has signed for it. So this has to be done manually. This is what we're all getting paid for. So not a feature that you're going to see in the future that this is done automatically. So we have to know the intersection. Usually I just bring this up so I know which of these signal groups are conflictive. Also, I've done this for this intersection probably 1,000 times. So just bear with me while I do these clicks. E2, E3, V3L not, this one not, this one, yes, this not, this not. And now V2, V3, that is conflict, this is not a conflict not, and this one is. V3 versus V4 is a conflict, P2 is not, P3 is against those pedestrians, and that should be it. I hope I haven't made a mistake. If you're watching this on YouTube, feel free to pause and check everything and see if we run into problems later, but I don't think so. Save and close. So now we have conflicts. Now we have the topology. We have the signal groups. Now finally it's time to get into the intergreen time calculation found under this button. What you're going to find after this opens is an empty table head. So far, this table has not been filled. We have to fill it by hitting the calculate button. When we've done that, we can talk about what we're seeing here. So we have two main columns here at the beginning, clearing and entering, and those show us signal groups, streams, and substreams. What is the difference here? So yeah, what we actually want to end up with is for every combination of clearing and entering signal group to have one intergreen time. That is what is here in the end. So these are like maybe the main information is kind of is colored in blue. So what signal group is clearing, which one is entering, what is the clearing distance, what is the entering distance, and based on the speeds that are in here, we're going to end up with the difference between the clearing and entering time is going to be the intergreen time. And the highest of these times is 6 seconds. So why are there different streams and why are there different substreams shown? So a stream conflict, here we have all the streams that belong to vehicle 1. We have straight and right. And here we have all the streams that belong to vehicle 2. We have left and straight. And so we have the different combinations of straight and left, straight, and right and straight. And in the last column, we see a substream. This means, so of course, the straight stream for V1 is actually 2 lanes. And on these 2 lanes, you can have different transport mode. To make this visible, so you understand what I'm talking about, we can choose to say, please show the substream conflicts. And before this, we just had these 3 stream conflicts. And now we have, for every stream, we have all the possible substream combinations between lane and transport mode. So instead of just 3 conflicts, now it's showing us, I think 16 is the number, 6 and 12 and 4. Yeah, 16 different substream conflicts. And out of all these 16, it's choosing the one with the worst intergreen time. If you're not sure, if you're looking at all these conflicts and say, which one was that again? Lane 1, B1, then you can click on this basic data button here and have both open at the same time. And you click on this conflict, for example, and it's going to highlight the two streams that are involved. And when you go through all of them, then you see where the time actually comes from. Depending on your guideline, depending on the country you've chosen, you will find different values in this table. You will also find different speeds that are predefined. Sometimes starting this with a different or creating an intersection with a different guideline at the beginning. You remember here where I chose RILSA 2015 English. Sometimes clicking on, let's say, Poland will only change the settings of these speeds and not the whole look and feel of this table. Sometimes clicking on a certain country, like for example, Israel, will change the behavior of all this because the Ministry of Transport of Israel is restricting a lot what you can do in this table. For example, there would never be allowed to change the length of a vehicle. In Germany, it's totally fine. If you're an engineer and say, okay, I have a lot of trucks here, so my vehicle length is going to be 8 meters and not 6, which is the default value, then this is going to be marked and it's going to have a consequence, and it's going to protect this line from recalculating. Then, of course, there are all these important, some more important, some less important parameters that you find in here. So let's say the intergreen time should always be bigger or equal than the yellow time, or something like that. Or clearing time and entering times and stuff like that. So there are certain cases here that can just be considered differently by checking a box. Behind all of these boxes, there is a city or a country or a province that wants it that way. So there's no right and wrong. There's just knowing who you're working for once. And once you figured it all out and maybe negotiated with, you can save it as a location default, if you might have guessed. Can also change all the speeds and all the approaches. Can change the speed for pedestrians, for bicycles, all of this. So once we're happy with these calculations here, we can fill our intergreen time matrix. So all the worst case intergreen times that were found in the table are now here in this matrix. And with this information, we could already let Lisa do a signal timing plan calculation. In the signal timing plan tool, calculate STP. And now all we have as a calculation option is minimum green times. Next. And what Lisa is doing now, it's creating stages and stage combinations. So this plan is now purely based on intergreen times and minimum green times. Something that is not reflected here is maybe some inner restrictions regarding offsets between certain signal groups, like that the pedestrian should always begin before the parallel vehicle group. This can be done in this offset matrix. For example, I would have the secondary direction to always begin at the same second. I would like to have this the parallel pedestrians always to be at least 1 second before their vehicle counterparts, like this, like this. I would like to have this signal, linker signal, always start at the same time, like the pedestrians it's supposed to protect. And then, of course, also when it ends, It should be, I don't know, be blinking for some 13 seconds. So with these matrices, I go back here and now I find that there's a little mistake based on that. There is always this automatic testing. And I see that I have to adjust my pedestrians a little bit so they are in line with that. And of course I can do changes here now graphically, right? I can push green time around. I can lengthen certain stages. I can move individual starts of green around as well. So P4 should be 1 second before that. V3 actually, this. I think I made a mistake in the matrix. This should be here. Do another test. Okay, blinker to P3. So this should start here in 32 and end somewhere around 60. And now I don't have any errors anymore. So there's this permanent check of if something is wrong in my plan, and I had certain offsets wrong. As you see, if I move this, maybe change the green time here a little bit and make it too short. Now you see I have a minimum green violation here. So everything is always permanently checked for compliance. So now that we have done the safety part, we can look at the evaluation part of the plan. So we know that it is safe now. It is the shortest possible cycle that we could find. But what is the shortest possible cycle when we have a given traffic volume? First of all, where do we get traffic volumes from? We can import data in certain formats. If you have counting data and you have large numbers of counting data for several intersections, you can import them here and you can create certain reports. Maybe I show this with a different example. This is the standard Lisa Town example, and it should have reports in it. The raw data imported here was data based on 15 minutes, and you can see these certain diagrams. And you can also add your own diagrams or yeah, save certain templates and then do an automated analysis like what is the peak hour here and export this as a volume for your evaluation parameters. In our case, we don't have that. We're going to just enter it manually. Let's assume somebody has given us the volume for a certain hour of the day and we want to enter it here. We hit the green plus here, call it peak hour, morning. And now that it's created, we can enter traffic flows into our matrix. You can see that it's formatting them automatically to a certain scale, coloring them. I'm just making these numbers up. Let's just assume we got them like this. This could be something. Now we can change the vehicle distribution, also the lane distribution, all kinds of stuff. So this is kind of the temporal evaluation parameter for every peak hour or every time of the day where we have data. We can define another demand or another flow. And then we have parameters for the evaluation, which are fixed. You can find them here under this ribbon parameters. And here you can enter, parameters about the width of the lanes, maybe add an inclination. Let's say we have, or a road gradient. Let's say we have 10% road gradient here, then it would appear like that. So this, of course, influences the saturation flow. I don't know. and put in turning radiuses, put an available length in front of right crossing. So everything from the geometry perspective that could influence the capacity of our intersection that will then influence the capacity calculation based on the German roadside manual. German roadside manual basically works, all the quality measurements are based on waiting time. So you usually end up with quality or levels of services from A to F. And behind every level of service, there's a certain waiting time threshold. So everything below a waiting time of, I think, 25 seconds on average is A, waiting and higher are B, and then and so on. Like there's a threshold for every level of service. And all this is based on the geometry and of course on the number of vehicles and the green time. So once we've made all these definitions here, we can go back to our signal timing plan calculation. Take some time. And now we see our plan that we have calculated before and was just based on what is the minimum cycle time. And we're ending up with a level of service of F now. How do we improve that? Let's calculate another signal timing plan. But this time, our calculation option will be that it's going to be based on a flow. Again, intergreen time, offset conditions. So this time we don't have to make these changes afterwards because it's got to factor in these offset matrices that we've defined before right away. Let's go with the German roadside manual version 2015, always until maximum cycle time. Now that the calculation is running with more parameters, it is also finding not as many combinations anymore. And what it's doing in the background, when you look at this minimum wait time, it's calculating signal timing plans for all these different cycle times, and then it's choosing the one where the waiting time is minimum, which is 73 seconds. So let's see how that looks. So now our level of service is mostly C, except for this pedestrian. What Lisa is doing, it's usually optimizing towards the overall average of the intersection. Of course, this whole intersection would be D now because it's always looking at the lowest level of service overall. So if we want to factor in the pedestrians, we have to shorten the cycle a little bit. And now we're at 66 seconds and now we have C. So you should also keep in mind, it's not the last word, this optimization of Lisa. It's not meant to be just one press of a button and then deploy and forget. There is still usually some optimization can still be done. But you just have to understand what the mathematical principle behind this first optimization is. So you see where there might be some room for improvement. So what else can we do here? Of course, there's all kinds of properties, meta information about this plan, the cycle time. We can change operating modes. Let's make it available in traffic actuated as well. Why not? What are the testing matrices that it's tested against? What is the evaluation flow? Could change that probably. And then if we wanted to make this work on the street, we need an activation point. I would say we take this second here, second 17. And now we can automatically calculate an activation plan and a deactivation plan. So with these plans, the controller knows how to get into the active state from the off state. And this is basically everything you do in Lisa S. You enter geometry, you enter a demand, you calculate intergreen times, and then you go with that into optimizing your fixed timing plan. And this would then be the outcome. And of course, would go into the batch print and say, okay, we want to print it all. Very nice. Or you send the data directly to your customer. Maybe something I haven't mentioned here yet is the time switch. Of course, you can also define what plan is supposed to be activated at what time of day. Simply adding commands, switching the intersection on, signal timing plan 1, then maybe at, I don't know, 6th, switch it to timing plan 2. And then in the evening again to 1, whatever. Now we only have 2 plans, but I think you get the idea. You can choose if traffic actuated shall be on or off. And then, of course, you can organize those day plans, have different day plans, put them into a week plan, and this can be deployed locally to the controller, or uh, if it's connected to a central, you can use this as a template or and put it into the configuration of the schedule of your traffic central. So that is the package or the functionalities you will find in Lisa S. Lisa M is adding the possibility to load coordinations. When loading a coordination, what is actually happening? You're loading several intersections at the same time. You're having all the informations about their signal timing plans and signal groups loaded in the background. And then you can put the main direction into time distance diagram. When you are manipulating this time distance diagram, you have the option to change the individual intersections accordingly. So this is a time distance diagram of the loaded intersections. Before I have given the information like what are the distances between the stop lines. This is information that you can probably get from Google, measure it from there and put it in here, or you have exact measurements. If your measurements are not accurate to the meter, that's not so important. It should be accurate to like 5 meters. I think that's where you can still get pretty good results, because we're usually talking about progression speed of 15, 13, 14 meters per second. So the resolution should be high enough so that it makes sense. So what can Lisa tell you now here about the quality of a coordination? So this is how the intersections on this corridor are coordinated. The information that you have to give about the intersections in the corridor is what are the signal groups that are entering from the side. We have already given this information here. If when you're starting new with a coordination, you can open up the schematic view here, and then you have all the information that you need to do this definition. And with that information, Lisa is capable of evaluating the quality of the coordination, and it's doing that by introducing platoons, which are shown here. Is actually pretty helpful to understand what is happening inside your coordination. When you have green, the greener the color, the denser the platoon is, or the denser the traffic. So this green bar here is indicating a platoon entering the coordination, and the fact that this green bar is getting lighter and lighter means that that part of the platoon is actually turning to the left and to the right, leaving the corridor to the sides. And then we have other platoons coming seemingly out of nowhere. Of course, they're not coming out of nowhere. They're coming from additional directions from the side street. So here you see that the platoon is starting from the side street. Then it has to wait because, of course, the next intersection is not coordinated to the side street. And then it's forming its own platoon in the main direction. So this kind of pink platoons, they're coming from the side street, and the green ones are on the main, already on the main corridor. And you can see here that in the end, at the last intersection, we're actually having a platoon that is mostly formed out of vehicles that at some point have turned into the into our corridor and are not really vehicles coming from the main direction. So this is additional information that at Schlottau and Bauer, it totally changed or substantially changed how people were planning coordinations. And it also explains why the optimization algorithm is tending to give a certain amount of free green, so to say, like green before the coordinated corridor, a coordinated platoon is arriving at the intersection, so that turning vehicles can actually vacate the intersection. Level of service here, C. This is based on the German roadside manual. We also have a performance index here. This is based on emissions caused by acceleration and deceleration. And then we have the average waiting time per vehicle in the direction of travel, opposite direction, and total. So what we can do is take this solution here and let Lisa do an optimization, and then we can see if it's better or worse than what we're seeing here right now. Analytical optimization, choosing a flow. Okay, we'll choose a flow. Let's hope that it was morning. And now we can optimize towards waiting time, maximum attempts, 50. What this is doing in the background, it's doing a certain optimization based on, or geometric optimization based on random starting solutions. One of them not being random, one of them being the one that we have just chosen here. And now it's going through all of these 50 solutions being optimized locally, leading to a local optimum. So the more time you have to calculate coordinations, I set it now to 50 attempts. You could set it to 500 if you have an hour of time, or 5,000 if you have even more time. As a rule of thumb, you could say usually one attempt should take 1 second or so. These 50 attempts were supposed to take about a minute. And you can see like 500 would be 10 minutes, 5,000 would probably be 2 hours. And the more attempts you allow, the better will be your final solution. The more probable it is that it is the overall optimum. I changed the color, that is why it. Okay. And here it says morning flow. Okay. So yeah, the waiting time is now 2.1 in one direction, 1.7 in the other, and 1.8 seconds overall for the morning flow. And for the other diagram, it was 3.2, 3.8, and 2.5. So it's a substantial improvement. And sometimes you will find some of the offsets maybe a bit counterintuitive, but when you go more into what is actually happening with the density of the flows, then you will find that it totally makes sense. What is the idea, or what the algorithm is trying to do, is actually to maximize areas with a dense traffic flow, because that means that the green time is actually used in a proper way. I mean, it's more like a result. It actually doesn't know about the density, but that's the outcome. It just knows about the waiting time or whatever criteria you are choosing here to be optimized against. One nice feature that was recently added is the time switch coordination. Unfortunately, I cannot show it to you in the English example right now because there are no switch commands available for the other intersections. Maybe I open a different coordination. In the German example, I think I have all this information in there. Just bear with me for a second. Let's take this one. The idea behind that is, as I said before, we're loading all the information of the different intersections at the same time. And of course, we're also loading their weekly schedules. And if you have a coordinated corridor, you would expect that all the intersections in the schedule, or at least the scheduled cycle times, should always be the same for all intersections. And if not, there should be a reason for that. But of course, these are just tables in these 6 individual intersections, and there might be a mishap. So that's why we introduced this new view where it shows you for every day of the year, when you click on it, what would be the schedule for that particular day. And this, we have this calendar here because of course you might introduce certain day plans or certain time periods for certain holidays and stuff like that. So it will take all that information and just calculate, okay, which plan is going to be active during which time of day for all the 6 intersections in the corridor. And if you have any mishap like here, it's a bit weird that the intersection in the middle is running at 90 seconds when everybody else is changing to 75. So maybe it does make sense maybe not, but you have the visual feedback and can control or double check if this is correct or not. So this is a very brief overview of the functionalities of Lisa M. Let's have a look now at Lisa XL. What is the functionality of that? So I will change for that to a different example where an actuated control is already introduced, because we would not have the time to actually do this right now. The idea of Lisa XL and of the logic editor is as follows. Traffic actuated control in Lisa is based on a method called OMTC, Open Method of Traffic Control. The idea behind that is that compatible controllers or controller manufacturers implement in their controllers a certain control scheme, and mostly this set of controller functions that are implemented as well in the here in the test site, in the virtual controller, as well as in the controller on the street. So if I use a function like tell me the time gap at a certain detector, it will work here on the test site, and it will also work in real life. And I can set up a certain controller logic using these controller functions, which are about 200 controller functions in different categories. The categories go by object that you would define in a control, for example, a detector. Yeah, now we have the German names here, but it is possible to load an alias scheme, because of course the real definition, this is usually German, but let me find the alias scheme. So you find the reason for this is because the original definition has been done in German. So as information technology goes, of course, the function names in the background somewhere remain German, but of course it's possible to replace these names with an alias scheme and use in English function names. So now as an example, detector function, there is a function called detector demand. It checks the demand of a detector. And with this function as, let's say, a tool or one piece of code, we can then define our logic. This is done in a flow diagram. This flow diagram is automatically translated by Lisa into source code that can either be C or can be Java code. This Java code also includes all the definitions we've made before in all the different tools here. So when we've defined a stage in the stage definition, then it will appear here. By the way, stage definition, something I haven't shown. I will just jump to that right after that. This stage definition or detector definition, they are all available now as objects. We built this diagram, and then we can see if it compiles. If it does, there is an unused logic, but that's fine, I guess. And once this logic here is defined, we can go to the test side and run it on our virtual controller. Here we have a little simulation. The simulation that we're using here, it's not perfect. There are certain definitions that haven't been done here for the conflicts of the secondary direction, but that's not really the point that we want to show here. We want to show that we can simulate the control that we have written in the editor, and we can also debug it. We can go step by step through it, second by second, and even switch to the logic and set a breaking point. Maybe I'll put it here. And now I can go back to my test window here and let the control running until we actually hit this breakpoint. And now I can go through the logic step by step, line by line, and see where it's actually exiting. I think that's pretty cool. And I take it back and it's gone. So where does this simulation here come from? So you see this simulation network. This is actually an export from the basic data that we've made in the beginning. So you see, I've opened a different example, but it's the same intersection that we've worked on before. It's basically just a click of a button exporting this network in this way. There are some steps that you can take to make it a bit prettier, introducing right of way for left turners, because of course they should basically stop in the middle of the intersection for the forthcoming traffic. There's an edit mode for that where you can edit the simulation. If you're not happy with the simulation and say, okay, this is just one intersection and it actually looks a bit basic to have cars move on predefined paths through the network and not have lane changes and all of that, then there is always the option to export this to Vissim. Also, there few modifications will have to be done from the export, but the export is pretty good for an initial to start working. And then you can also combine several intersections and also run several virtual controllers in parallel. And when you do changes in the logic, changes in the parameters, it's just one click of a button updating that in your Vissim simulation and testing and monitoring your progress. Yeah, I jumped one chapter here, which is the definition of stages and stage transitions. Of course, if you are using the open method of traffic control, usually you're going to be working on stage controls. Let me go back to the example that we have done together. For your understanding, I think before in the old licensing model, stages and stage transitions were still available in the basic version of Lisa. Now they have moved to the XL license. So I wanted to start with them after presenting the Lisa M functions, and then I simply forgot that they also belong to Lisa XL. So everything we're looking at now is Lisa XL, including the stage definition, 1, 2, 3 stages. Yeah, basically defining stages is as easy as that. Then you can position them here on your page. Technically, we have to tell Lisa what the signal groups shall be part of the stage by right-clicking into this table down here. As soon as we click on a certain signal group, all the conflicting signal groups will be marked with an X, cannot be chosen anymore. So it's stage 2 left turners and stage 3 or P3, and also this blinker. And yeah, now we can do all kinds of modifications to the layout here until we're actually happy and find it comprehensive and understandable what we're doing here. So this is basically just cosmetics. You can change the line style, you can change the font, you can even change the stage symbol from a circle to a square. All of that is possible. Now to go on with stage transition definitions, we can define which stage transitions we want to be possible. These are then used later by Lisa to check which stage transitions it shall generate automatically. When we're in the stage transition module, we can choose an activation stage, but basically now in the Lisa 8 look and feel, we have everything at one. You can see everything at a glance, the diagram, the stages, the properties of the stages, and the matrix of signal groups and stages. So once defined, we save and close. We can now jump into stage transitions. And all we have to do now is do automatic stage generation. He says checking for us. Hey, I found 6 stage transitions over there. None of them exist. Maybe we should calculate them. Minimum green time offset conditions shall be considered. Okay. And now we have these stage transitions here. Why are they called PUE? Because I still have the German, let's say, name for it. General prefix for new plans is PUE. When we're talking about stage transitions, I might want to change this to ST. Okay, and now do this again. And now they're called ST, stage transition 3.2, and so on. Same goes with signal timing plans and stages themselves. There is always a default how you want to name them. Let me show you. We have this batch print function here. So for example, all the data that we've entered, signal group tables, auxiliary signals, signal head allocations, intergreen time calculation, offset conditions. All this can be changed. There we are. So we have our own cover sheet. It can be changed in the settings of Lisa. There is also the possibility of, so these are basically just all the exports or reports coming out of Lisa. You can also add your own free text or whatever when you go to, oh yeah, cover sheet would be here, of course, where you can change what data should be appearing. The logo can also be changed at some other point. And under documentation, you have the possibility to use this word plugin where you can basically enter free text, also add paragraphs, and all this is also then considered when you do the batch print, and your pages will update accordingly. And everything is there, so facilitated that at the end it should be just one press of the button when everything is configured in the right way.
Thanks a lot for joining us today. And as always, we are at your service if you have further questions. Please contact us at service@schlotauer.de if you have any technical questions, or if you want a quote, an offer, have any sales-related questions, then please contact us at lisa@schlotauer.de. Thanks and have a nice day.
So all the data that we have defined so far will appear here in our batch print view, where you can see all the data on its respective print page. You can change the title, you can change the page number, you can even change in the settings what kind of information do you want on this page to appear. This is very handy, like in the end, when you wanted to structure your documentation of the intersection, like what do I want to print in which order, how shall it appear?